Good morning or good evening, whenever you're watching. This is Professor Tierney sending you your first video of content that we were going to cover in lab this week. You might hear I'm a little congested, didn't want to spread anything to my students who I know it's hard enough to be in school, and being sick at school is worse. So I am keeping my germs to myself. I think what I'm going to do is record this in 3 shortish videos to give myself a break. And then if you want to watch them all and binge them, binge Tierney, go for it. I'm going to be using my software for writing on my notes. So hang on just a second. I'm going to share that. Okay, so I am on page 10 of chapter 12. And we covered in class naming aldehydes. Now we're going to talk about naming ketones. Um, and ketones and aldehydes are very similar. So ketones also contain that carbonyl. Hold on, I haven't used this program in a minute. This carbonyl right here, C double bond O. In aldehydes, if you recall, that C double bond O, that is at the end of the molecule. So the carbon is also bonded to a hydrogen. In ketones, that carbonyl, C double bonded to O, is somewhere in the middle of the molecule. So that carbon is double bonded to the O and then has single bonds to 2 other carbons. Your smallest ketone is propanone. So remember that prop is 3 carbons. And then we have butanone, which has 4 carbons. These 2 ketones are the only 2 ketones that do not need a number in front to designate the location of the ketone because they only have one location the ketone can go. For butanone, remember that we could call it 2-butanone, but it's unnecessary because that ketone can only go in that number 2 spot. If I were to put it in the number 3 spot, we would change it to number 2 because we always start counting from the side closest to the functional group. The third example here is 3-pentanone because it's on the 1, 2, third carbon in. All of the nomenclature rules are the same that we've been learning. So this is going to be a nice review of a lot of the other naming. The carbonyl, that functional group, always gets the lowest number. And then if that carbonyl is on a cyclo molecule, we always assume that that is coming off of carbon 1, and then the substituents get their lowest numbers possible. So let's take a look at some examples. So 2-pentanone, I bet you can do that one on your own. If we were in class, I'd give you a moment to try and draw it on your own to see how much you remember. For purposes of the video, go ahead and pause me if you want to go and try it. But pent means we have 5 carbons. So 1, 2, 3, 4, 5. And then I have my carbonyl coming off of the second carbon. If you want to draw the condensed, excuse me, I have a very runny nose, so I will be periodically wiping my nose because it just goes. If you want to draw the condensed, what you're going to see is that when you add that double bond O onto that carbon, that now takes up all of the bonds that carbon can have. Carbon can only have 4 bonds. So when you have a ketone in this middle of a carbon chain, that carbon never has a hydrogen attached to it. It's always bonded to 2 carbons in addition to that oxygen. So that would be our 2-pentanone in both respects. Our next one is 3-chlorocyclohexanone. So cyclohexanone means we're going to have 6 carbons in a ring. resist the urge to draw the double bonds to make it into a benzene because this is not benzene. Cyclohex means six-sided, no double bonds unless it's cyclohexene, then it would have one double bond. You can put that carbonyl oxygen onto any carbon, and that automatically becomes carbon number 1. And then we're going to put a chlorine on the third carbon over. You can go in either direction, clockwise or counterclockwise. So I'm going to add it right here. So that is our 3-chlorocyclohexanone. Okay, let's go the opposite way. I'm giving you 2 structures. If we were in class, I would give you this moment to try naming these, and then we would go over them together. In the interest of time on a video, if you want to pause it and give it a try, I very much encourage that. I'm going to go over it. Let me change my color to a blue just to kind of differentiate. So on our first one, our longest parent chain right here, this is 4 carbons long. We start numbering so that the functional group gets the lowest number, which means that we need to start counting from the left. 1, 2, 3, 4. So that would mean that this is butanone. Now, butanone, we do not need to put a number because there is only one spot the ketone can go on. However, if you called it 2-butanone, I would not mark that wrong. So I'm just going to put that in parentheses. And then we do have another functional group. I'm just going to differentiate that here. Here, excuse me, not a functional group, a substituent, my mistake. We do have a substituent in addition to our functional group, which was the ketone. This substituent is a methyl group. It's coming off of our third carbon. So we would call this 3-methyl-butanone. If you put 3-methyl-2-butanone, that would be okay with me as well. Okay, let's try the next one. Our next one, our parent chain, is that cyclohexanone again. We know that it ends in unknown because our functional group is that ketone. That automatically becomes carbon number 1. So we've got cyclohexanone, a known. I didn't really emphasize this to start, but a known is the ending for a ketone. So we would have added that together on the blue sheet for ketone as the ending, a known. So cyclohexanone, we're going to number in the direction. Sorry, my puppy is woofing just a little bit in the background. We're going to number in the direction that gives us the lowest numbers for our substituents. So we could go clockwise or counterclockwise. If we went clockwise, let's just do the math. We're trying to get the lowest number. So if we went clockwise, bromine would be on 2, 3, 4, 5. That methyl would be on 5. If I went counterclockwise, the methyl would be 1, 2, 3, and the bromo would be 6. So it looks like going clockwise gives us a smaller set of numbers, so that's what we're going to do. And we see that we have Br, that's going to be a bromo. Our CH3 is a methyl group. So we're going to list those alphabetically. So bromo is at the number 2 spot, so we call this 2-bromo. And then we have methyl at the 5 spot. Let's see if I can fit this in. 5-methyl. Apparently my puppy does not like ketones. So that is how we name ketones. Let's also cover the physical properties, specifically solubility of aldehydes and ketones. So aldehydes and ketones both have this carbonyl group. If we look at the C double bond O, as in terms of polarity, we see that Oxygen has a 3.5 electronegativity. This is on our purple sheet. Carbon's a 2.5. So if we subtract those, the difference of 1.0 means we have a polar covalent bond. Now the oxygen has the higher value, so that would be a delta negative, and the carbon would be a delta positive. This is nice on the video. These are in color on your handouts. They're black and white, but we have ethanal and propanone. So this is our carbonyl in this molecule, and this is our carbonyl in this molecule. And then we're showing that the oxygen with a delta negative is sticking out from the molecule. This is a spot where it can hydrogen bond with the hydrogens in water molecules, and that will create solubility. Same with a ketone, has that double bond to the O, and that creates a spot for hydrogen bonding. So that makes it soluble. However, all of the areas that have those alkyl groups, and let me just change the color. So here in ethanol, here we have these carbons coming off. Those are, if you recall, CH bonds, those are nonpolar. So those are not going to be soluble in water. So once again, we see this push and pull of solubility between the functional group, which does have hydrogen bonding capability, and then the carbons, which don't. So the more carbons you have in a ketone or an aldehyde, it becomes less soluble in water. And in general, when we compare aldehydes and ketones to alcohols, remember that alcohols have this OH where the oxygen has a delta negative, the hydrogen has a delta positive. And so there are two sites for hydrogen bonding on an alcohol that are coming off that carbon, whereas in carbonyl-based functional groups like aldehydes and ketones, there's only one spot. So aldehydes and ketones are less soluble in water than alcohols, and this is because they have fewer hydrogen bonding sites. So that finishes up section 12.3 for us. I'm going to have section 12.4 in 1 or 2 videos. We'll see what I'm up for. And I will send those out later. I'll post those later. Um, we can go over any questions that you have in class if you like. I do want to give you opportunities for asking questions, or feel free to send them via email to me so I know ahead of time what kind of questions you have. All right, thank you for watching, and I appreciate your flexibility while I am not feeling well. And now I need to turn off my video.